Swayam Prabha. Digital India. Educated India.
Welcome friends to this fourth lecture of our module 9 or week 9, and in this week we are talking about the pollutant and soil solution interactions. So, in our previous 3 lectures we have discussed several aspects of pollutants and their interaction with the soil solution. We have discussed the different dynamics of the pollutants which are soluble in water and how they can interact with different phases, and also we have discussed the heavy metal dynamics in the soil solution. We have discussed we have discussed different acid base equilibria and other solubility equilibria. We have discussed the acid rain effects, and also we have discussed the solubility of aluminum from the aluminum organic matter complexes, and also we have discussed the dissolution of gypsum in the sodic soils. So, in our last lecture, while wrapping up, we have talked about the ion pair effect in the dissolution of sodium. So, let us see what is ion pair. Now, ion pairs in chemistry, ion pairs are basically formed when a cation and anion which are present in a solution of an ionizable substance come together to form a discrete chemical species. So, again when the anion or cation which are present in a solution of an ionizable substance come together to form a discrete chemical species. And there are 3 distinct types of ion pairs depending on the extent of solvation of the 2 ions. We can see here in this picture, one is the fully solvated ion pair where these cations or anions are fully solvated, and then we can see that solvent shared ion pairs. You can see the solvent are shared between these ion pairs, or solvent separated ion pair, or cation outer sphere complex. So, examples so basically this is the solvent shared ion pair. And again the third category is basically you can see when the cations and anions are basically in their contact of each other. So, that is called the contact ion pairs. So, it is fully solvated ion pair, this is solvent shared ion pair, and this is contact ion pair. And so, this ion pair effect has a a considerable influence in the gypsum solubility in the sodic soil. So, if you see the kinetics of calcium dissolution from a gypsum sample in various salt solutions, we can see this type of relationship. This relationship is basically showing the salt effect on gypsum dissolution. In other words, it is calcium dissolution of gypsum. So, the salt effect on gypsum dissolution shows the dissolution kinetics of gypsum samples in sodium chloride and magnesium chloride solution. So, you can see here there are different concentration of sodium chloride. So, for example, this one is 10 millimole per kg concentration, and also this is 40 millimole per kg concentration, okay, and this is 60 millimoles per kg concentration. And as far as the magnesium chloride is concerned, we can see here this is 20 millimole per kg concentration, and this is basically sodium sulphate which is showing 20 millimole per kg concentration. So, basically this is showing the calcium dissolution or gypsum dissolution dynamics with respect to time which is basically influenced by different concentration of different salt solution. So, it appears that dissolved amounts at equilibrium are clearly related to the ionic ionic composition of the solution. Okay. So, depending on the ionic composition, we can see that dissolved amounts are at equilibrium. So, what are the other inference from this figure? We can see that the dissolution rate is only apparently different. So, we can see the dissolution rates are basically having the similar type of the changes of calcium dissolution rate is showing the with respect to time is basically showing the similar type of trend, and if we basically normalize these graphs, we can see these representations. So, basically the normalized representation allows all the experimental points to fall on a same curve. So, basically all the individual curves when we normalize will basically form in this will fall in this curve. So, basically we see that the concentration ratio of which is denoted by the C by Cl is basically or C by C sorry is basically increase with the passing of time. So, as the time increase there is an increase of this concentration ratio. So, basically in this figure it is showing the kinetics of calcium dissolution from a gypsum where the ratio of dissolved calcium concentration to its equilibrium value. So, basically this is calcium equilibrium value as a function of time. So, we can see this ratio is continuously increasing when we are increasing the time. So, this dissolution kinetics can be expressed by the formula or the relationship given by this Schwarzenegger, and this relationship basically shows dm by dt equal to Ks multiplied by C dash sat, so saturation minus C equal to Ks over C sat 1 minus C by C sat. We basically the this C basically stands for calcium concentration and this C sat is basically the equilibrium value. So, this relationship can be expressed in terms of this relationship, this mathematical relation. So, we have covered the dissolution kinetics of gypsum. Now, it is time to discuss another very important issue, that is sludge and its effect on potentially toxic inorganic trace element solubility. So, all of you must know about the sludge. So, what sludge, that it is a semi solid slurry that can be produced from a range of industrial processes, from water treatment, wastewater treatment or on-site sanitation systems. So, you can see this is the this is the semi solid slurry called sludge, which can be produced from different industrial processes, anthropogenic processes, water treatment or wastewater treatments or on-site sanitation system. So, you can see this this is frequently, this can be frequently seen especially in urban areas. So, this is a potential source of pollutant because it carries huge load of different organic and inorganic pollutants. In the inorganic pollutants, the heavy metals and trace elements are important, and as far as the organic chemicals are concerned, there are different toxic organic chemicals which are loaded in this sludge. So, obviously, the interaction of sludge with the soil system is very important, is very important and needs to be learned if we wants to have a comprehensive idea about the pollutant and soil solution interaction. So, what are the different trace elements in the sludges? I have already told you that the sludge contains different trace elements. So, sludge from municipal origins are disposed of land and in large amounts in small areas around the water purification plants or in relatively small amounts spread over large areas where it is used as a additional organic manure in farming practices. So, again these sludge are basically generated from these municipal origins and disposed of on the land in large amounts in the small areas. So, for example, nearby some water purification plants or in relatively small amounts spread over the larger areas, basically as a mean of addition of organic manure for farming practices. Now, the sludge of municipal origin are characterized by the presence of a large number of potentially toxic trace elements. Now, these municipal sludge are loaded with different heavy metals or trace elements which can create considerable toxicity in the soil. So, let us see those. If we consider the management of the sludges, the management of sewage sludge is one of the environmental problems which are not fully solved yet. Obviously, there are some problems. So, the management of sewage sludge is a big challenge for the environmental scientists. Now, in many areas, the abundance of heavy metals in these sludges make them inadequate for agricultural use. Obviously, you do not want to add this manure, you add these in terms of manure in the field to create further problem, to encourage the bioaccumulation. So, in many cases this abundance of these heavy metals are the reason, that is why due to the presence of huge amount of organic matter which is considered to increase, which is expected to increase the natural fertility of the soil, it is not generally used because of the presence of this heavy metals. Also, they are dumped on uncontrolled landfills. So, the landfills are the regions where you can see the municipal solid wastes are basically dumped. So, in this dumped in these uncontrollable these uncontrolled dump sites or landfills, you can see huge amount of these municipal sludges are being dumped. So, the influence of this practice on the soils and groundwater quality depends to a large extent on the texture and composition of the soil on which these sewage sludges are dumped. It is quite natural because of the different soil physico-chemical properties. The movement of heavy metals or other organic chemicals from the sludge is impacted by the physical condition or physio-chemical condition of the soil on which it is dumped. If the soil texture, based on the soil texture, the movement or mobility of these heavy metals can be influenced, and also the organic chemicals also can move through the soil column based on the different soil properties. So, soil texture and composition are very, very important for the mobility and mobility of these heavy metals or trace elements or organic chemicals from the soil to groundwater. If the texture is sandy, obviously there will be more movement of these toxic or organic chemicals or heavy metals down to the groundwater and ultimately creating the groundwater pollution. So, different trace elements in the sludges, if you see here one table which published by Cheney in 1983, we can see that these are the concentration of different heavy metals and trace elements. PB lead is a heavy metal, okay, and so these are the trace elements, and let us if you see the concentration, they generally show a wide range of variability, starting from if we consider this arsenic, it shows wide range of variability from 1.1 ppm or milligram per kg of dry sludge to 230 ppm. Then cadmium, which varies from 1 to 3410, and copper, which varies from 11.3 to 2490, and so on so forth. As compared to the lead, in respect to the lead, you can see wide variations starting from 13 ppm to 26,000 ppm. In case of zinc, it varies from 101 to 49,000 ppm. So, 49,000 ppm means 4.9%, which is quite high. So, similarly iron from 1000 ppm to 154,000 ppm. So, you can see that how this sludges shows a wide variability of these stress elements, and sometime which is beyond the permissible limit, and these are the median values of those data. So, the soluble organics which are originating from sludges may retain the inorganic trace elements in a non-adsorbable form, which is mainly as anion or neutral species. So, the soluble organics which are also originating from sludge may retain in the inorganic trace elements. These inorganic trace elements basically retain in the sludge in a non-adsorbable form, mainly as anions or neutral species. Now, the inorganic forms associated with organic matter could include different forms. What are those? Metallic particles, it could be metallic particles, relatively pure precipitates. What are those relatively pure precipitates? Phosphates, carbonates, sulfides or silicates. So, you can see these are the relatively pure precipitates like phosphates, carbonates, sulfides and silicates, which you can see are associated with the organic matter in the sludge. Also, this sludge contains solid solutions resulting from co-precipitation with precipitates of iron, aluminum and calcium, or as metal ions strongly adsorb on the surfaces of iron, aluminum and calcium minerals. So, you can see that these trace elements can be present in the sludge in different forms, and also metals may be present in soils in many forms. So, basically you can see that either they can be these trace elements can be present as metallic particles or precipitates or solid solutions or or co-precipitations, so or strongly adsorbed. So, there are different forms in which they are present in the sludge and ultimately creating the environmental problem. So, this is another data which you can see that produced by Young et al. In 2017. We can see that the content of heavy metals, for example, copper, lead, zinc, cadmium, nickel and chromium, they are how they are varying in different parts of the study area. So, we can see that for acidic soil, these are the threshold values, that means the permissible values. For example, 800 ppm for copper, 300 ppm for lead, 2000 ppm for zinc, 5 ppm for cadmium, 100 ppm for nickel and 600 ppm for chromium. And for neutral and basic soil, the corresponding values are 1500 ppm, 1500 ppm for copper, for lead it is 1000 ppm, for zinc it is 3000 ppm, for cadmium it is 20 ppm, for nickel it is 200 ppm, for chromium it is 1000 ppm. So, if we consider the mean values which they calculate from different areas, you can see that as far as the cadmium is concerned, it is showing higher than the threshold value for the acidic soil in case of acidic soils, and also the nickel concentration is quite high, which is around 600, mean nickel concentration is 692.94 ppm, which is quite high than the threshold values of both acidic soil as well as the neutral or basic soils. As far as the chromium is concerned, the values are less than the threshold values of acidic soil. So, obviously, that shows the wide variation of different heavy metals which are present in the sludge and how they can and some of them are above the threshold limits, permissible threshold limits. Now, if you see the complexation with soil organic matter, in the metal organic matter complex, a general decreasing order of complex stability was stated by this two scientists, Schaefer and this Shastable in 1982, and this is that the decreasing order of complex stability can be found when with the highest of Fe3 plus, aluminum 3 plus, then copper, then lead, then Fe2 plus or ferrous, nickel, cadmium, zinc and manganese. So, this is basically showing the decreasing order of complex stability. So, obviously iron has the highest and manganese has the lowest. So, the type of organic molecules which are involved in forming the soluble complexes are basically oxalic acids, citric acids, malic acids, tartaric acid and many other acids and aliphatic and aromatic compounds. And these these acid basically complex with these heavy metals in the sludge. So, another important graph is there which was shown by McBride in 1989, which shows the relative importance of various organic acids as a function of the complexation of metal and pH. So, you can see the log of concentration if you plot that in the y axis and pH in the x axis, that shows there are two metals, one is zinc, another is copper, and there are two types of organic complexes, that is catechol complex and salicylate complex. For both the elements, we can see that up to pH around 5.5, the concentration, the binding capability of zinc salicylate is higher than that zinc catechol, and then when this threshold level is achieved, then the zinc catechol showing the higher complexing ability than that of the zinc salicylate. In case of copper, it shows for the same at pH 4, it shows quite high complexing capacity, where up to pH around 5 these copper salicylate shows highest higher binding capacity or complex forming capacity. However, when the pH goes beyond 5, then the complexing capacity of copper catechol is increased than copper salicylate. So, that shows the importance of pH importance of pH for determining the complex formation of different organic acids with the with the metals, and this plays a very important role for these metal dynamics of the heavy metals in the sludge when they are dumped into the soil surface. So, if you see that the copper catechol 2 plus, so basically these species basically dominates over the copper catechol 20 species above pH 7.6. So, if you see that pH 7.6, around this pH 7.6, this copper catechol dominates over copper catechol 20 species, and copper is precipitated to be almost totally complex with catechol at high pH, and catecholate ligand is better electron donor than that of salicylate ligand. Also, we have seen that the metal organic complex can modify the solubility of metals in the soil solution, and consequently their transport in the soil profile. And this basically this solubility modification was assumed to be the explanation of the increased cadmium transport in drainage water following the sludge application. Remember, the sludge composition basically includes, besides the organic ligands, free salts which can form the complexes with the potential pollutant stress elements. So, let us see the impacts of redox process on metal solubility. So, if you see that the dissolution of the trace elements into the soil liquid phase and their redistribution into the porous media between the land surface and the groundwater is also affected by the redox reactions. We have already discussed these redox reactions extensively in our previous lectures. So, the redox process could occur in the whole soil profile under the saturation or drying conditions. Now, in case of unsaturated soil, the process of reduction and oxidation, this redox reaction proceed simultaneously at the aggregate soil level, and reduction into the soil aggregates and oxidation at the aggregate surface. Obviously, at the aggregate surface, that is more in direct contact with the air. So, obviously, there will be oxidation, and in the aggregate, when there is less contact with the external oxygen or air, then obviously there will be reduction. So, we can see in an unsaturated soil, the process, the redox process basically goes side by side simultaneously at the aggregate soil level. And you can see this is the this is the picture of a redox reactions which is undergoing in the soil, which is you can see the coloration, the change in coloration in the soil as a result of redox process. So, these this shows very important implication for metal solubility. Now, it is known that the heavy metals are less soluble in an aqueous phase in their higher oxidation states. So, the reduction oxidation in soils are basically enhanced by either biological process or a chemical catalysis, and it also affects the heavy metal solubility again. So, we know that the heavy metals, when they are present in the higher oxidation states, they are less soluble in aqueous phase. So, when the redox reaction in the soil are basically biologically mediated. So, these biological or chemical catalysis is generally used to enhance this redox process. It also affects the heavy metal solubility by changing the oxidation status. So, this is how the redox potential or redox reaction has a profound influence on the heavy metal solubility, and this is playing a very important role for heavy metal contamination when we are applying the sludge in the soil surface and their mobility. Now, if you see the redox potential of the solubility of iron, we know that the electron activity in soil controls the ratio of Fe3 plus to Fe2 plus in solution according to the reaction. That is, we know that according to the reaction Fe3 plus, when there is an electron, there is a electron, then it will be converted to ferrous. So, ferric will be converted to ferrite by after accepting an electron, and here the log K value is basically 13.04. Now, we know that the logarithm of this reduced species over oxidized species equal to this log K0 minus P. We already know that. So, basically inputting this value of log K will get this reaction. Let us consider this reaction 1. So, logarithm of Fe2 plus over Fe3 plus equal to 13.04 minus P. Now, when the Pe value is 13.04, obviously, so this total right hand side will become 0. So, obviously, in that condition this ratio, that is Fe2 plus to Fe3 plus, is become in unity and change. So, basically changing Pe by 1 unit basically changes the ratio of Fe2 plus to Fe3 plus by tenfold. So, this is basically the redox potential on the solubility of Fe. So, similarly, we can see the implication of redox potential on the solubility. So, basically when the Fe3 plus converts to Fe2 plus, obviously their solubility is increased. Fe2 plus is more soluble, ferrous is more soluble than ferric. So, this is how when the change in the redox potential results in the changes in the solubility of iron. So, this is also showing a very good relationship between the pH and activity of Fe2 plus and Fe3 plus ions. So, it is clear that as we decrease the redox then there is an increasing the activity of Fe2 plus in the equilibrium with soil iron. So, basically when we are reducing the redox, that means the redox potential is decreasing. When the redox potential is decreasing, the activity of Fe2 plus in equilibrium is increasing because their solubility is increasing. We know that iron will be converted, Fe3 plus or ferric will be converted to ferrous Fe2 plus by accepting an electron. So, basically when there is a reduction occur, when the redox potential is decreasing, the Fe3 plus will be converted to Fe2 plus, and as a result of that their solubility will increase and their activity will increase. So, the lowest dashed line, as you can see in this picture, this lowest dashed line, this is the lowest dashed line. This represents this Fe2 plus at this Pe plus pH value of 20.61. Okay. Now, at this redox potential, the activity of Fe2 plus and Fe3 plus become equal at pH 7.57. So, this is the pH 7.57 when the activity of these Fe2 plus and Fe3 plus becomes equal. Now, remember that from this graph that the Pe plus pH values, as you can see, this is the Pe plus pH values of soil is generally lower than that of 20.61. So, as you can see 18, 16, 14, 20, 12 and 10. So, this Pe plus pH values of soil is generally lower than 20.61, and the activity of Fe2 plus in soils is basically is most often greater than that of Fe3 plus. So, this graph shows us this implication. So, basically when we are reducing the low redox potential, it is increasing the Fe2 plus activity in the soil solution. Here we can see the lowest dashed line represents the Fe2 plus at P plus pH of 20.61. At this redox potential, these activities of ferrous and ferric become equal at pH value of 7.57. We can see here it is becoming equal, and since the P and pH of the soils, this P plus pH in the soil is generally lower than that of 20.61, as you can see 18, 16, 14, 12 and 10. And the activity of this ferrous in soil is most often greater than that of Fe3 plus. So, this is the relationship between the logarithm of activity and the pH of the soil solution. So, friends, we have learned some important aspects of sludge and how different trace elements are present in the sludge, and what are the different conditions which are influencing their mobility in the sludge, what are the sludge management, what is the difficulties in the sludge management, why we are not applying the sludge as a manure in the agricultural fields. So, I think you have gathered some new knowledge from this lecture. Please feel free to email me if you have any queries. I will be more than happy to answer your queries. So, let us wrap up our lecture here, and in our last lecture of week 9 we will be talking more about polycyclic aromatic hydrocarbons and their properties, and how their solubility, generally some insights on their solubility in different solvents. So, let us wrap up our lecture here, and let us meet in our last lecture of week 9 to discuss polycyclic aromatic hydrocarbons in details and their and their different properties and their interaction with different solvents. Thank you very much.